6.5 Trigonometric form of a complex number. Well, you should learn how to plot complex numbers in the complex plane to find absolute values of the complex numbers, write trigonometric forms of complex numbers, multiply and divide complex numbers, use the Moivre theorem to find the power of complex numbers. So here's a complex plane. It's actually very simple, right? If you have your normal xy axis in a complex plane, we're making the x the real axis, we're making the y the imaginary axis, as you can see here. So if you have a point like 3 plus 2i, it's the same thing as this graphing the point 3, 2, right? I is the y, x is the real. So that's a complex plane. If you want to find the absolute value of a complex number, that's just a distance from the origin. So we're just going to do the same thing we did with vectors. We're going to take the x value squared plus the y value squared, but without the I. Okay, so this is our first one here. Plot this complex number and then find its absolute value. So we're going to plot it first. So here's our real and our imaginary. Here's our grid. This is essentially the same thing as this graphing negative 2, 5. So you can go negative 2 in your real and then 5 in your imaginary. That's negative 2 plus 5i. Now if I want to find the absolute value is literally just this guy. How far is it from the origin? So if you want, you can make a triangle out of it. But we're just going to use the formula. Absolute value is just going to be square root of a squared plus b squared. This is a and that is b. Remember, we do not include the I. So it's going to be square root of negative 2 squared plus 5 squared. So square root of 4 plus 25. So square root of 29. That's the absolute value of that complex number. So now that we know that, we can do the trig form of a complex number, right? If you look here, let's say here's our complex number. We could write it in trig form because here's our x value. Here's our y value. So a could be rewritten as our point AB could be rewritten as the point r cosine theta, right? Cosine goes with the x value, and then multiply by the radius, and then r sine theta. So your x value is this r cosine, and your y value is r sine. Remember, sine e cosine x, and we could write it like this. Or another way of writing a trigonometric form is this right here. It's r parentheses cosine plus I sine theta. This is essentially your a and your x and your y, or your a and your b, and then you're times it by the length of the radius. So that is the complex form of that is a trigonometric form of a complex number. R times cosine theta plus I sine theta. And if we have that, we have to know how to find the components of it, right? We got to find two things. We got to find r, and we got to find theta. Well, r is the radius. It's the absolute value of it. So we're just gonna do a squared plus b squared, right? Because it's like when we did the problems up here, right? R was just the length of that. That's just the radius. That's what the absolute value is, just the radius. So that's how we find r. Then how we find our theta. You gotta remember, so we did earlier, tan of theta equals b over a. So just like before. We're trying to find the angle here, right? It's going to be opposite of adjacent, which is tan. So that's why tan equals b over a. So those are the components needed to find trigonometric form, also known as polar form. We're going to do more of that later. But so that's how, if you want to write a complex number in trigonometric form, we need to find our radius. So we're just going to do absolute value. That we're going to find like Pythagorean theorem basically, and we're going to find the angle. So first problem here, write the complex number z equals negative 2 in trigonometric form. So first, let's write it proper complex form, 0 minus 2i. Right, so if I want to write it in trigonometric form, that is this r cosine theta plus I sine theta. So we have to find two things. We have to find the r and the angle. Okay, so first the r, it's just a squared plus b squared. So 0 squared plus negative 2 squared. Keep in mind when we do this, you don't include the I. So you're going to get square root of 4, which is 2. So my radius is 2. And then to find the angle, we're going to do tan theta equals b over a. So in this case, that's going to be negative 2 over 0. That's undefined. So how do we do this? Well, let's draw. Where is negative 2i at? Negative 2i is down here. Right, because it's 0 on that way. So what angle is that? Well, inverse tan, right? Isn't that the angle of negative 90? If I want that in degrees, we're going to add 360, and that's going to be 270. So that's my angle, which makes sense. Remember, tan is undefined on the y-axis. So there's my angle, there's my r. So we have our answer. Z is equal to 2 cosine of 270 plus I sine 270. And that's this written in trig form. So let's do another one. This is for practice. Okay, so again, we want to write it in this form. R equals R cosine theta plus I sine theta. Right, we got to find two things. We got to find R, which is just 2 squared plus 2 square root 3 squared. Technically negative, but the negative goes away when you square it. And then tan of theta is equal to b over a. So negative 2 square root 3 over negative 2. Okay, this first one here, we're going to get 4. Now, the way this one works is you're going to square both of them. So we're going to get 4 times 3. Right? Think about 2 square root 3, basically times 2 square root 3. What would you get? You would get 4 square root 9, also known as 4 times 3. Same thing's going on here, right? 2 times 2 is 4. 2 squared is 4. Radical 3 squared is 3. So 4 times 3 is 12. So we get square root of 16, which is 4. There's my r. Now theta, we have this, right? B over a. Well, negative 2's cancel, so we have tan of theta is equal to square root of 3. Inverse tan of both sides. And if you use this in your calculator, inverse tan is going to be right here, right? Positive, negative. Tan is right 3 over 1. So we're going to get 60 degrees. But there's a problem. There's one thing we got to check. We have to make sure we're in the right quadrant, because this is tan inverse only goes quadrant 1 and 4. What quadrant is this in? So graph it. If you graph z, right, we're going to go negative 2 and negative 2 right 3. So we're going to be over here. We should be in quadrant 3. That's not the correct quadrant. So how do you fix it? Fixing tan is really easy. All we have to do is add 180 to go half a circle to the right quadrant. So since we know it's the wrong quadrant, we're going to add 180 to it, and we're going to get 240 to be in the correct quadrant, right? Because 240 would be right here, 180 plus 60. And there we go, that's our theta. So we're going to get 240, 240, and we get z equals 4 cosine of 240 plus I sine 240 degrees. Okay. How do I go the opposite? How do I write a complex number in standard form? Well, that's easy. It's more straightforward. You just simplify it. So over here we have to figure out what cosine of negative pi over 3 is. So here's 0. Negative pi over 3 will be over here. It's over 3, which means it's a 60 degree angle, which makes this negative 3, 1, and 2. The negative 3 should be negative because you're going down. Cosine SOHCA is adjacent rod, is 1/2. So all this guy is 1/2. Plus I sine of pi over negative pi over 3, same picture. Negative pi over 3 is going to be radical 3 over 2. Negative radical 3 over 2. And then we distribute the square root of 8. Goes into everything. So I get square root of 8 over 2 plus negative 24 over 2i. There we go. I could break down 24 if I really want to, right? 24 is 2 times 12, 2 times 6. So 2 square root 6. It's about the same though. You can also do this. I also break down radical 8 actually. 8 is 2, 4, 2, 2. So 2 square root 2. I should break down both of them honestly. 2 square root 2 over 2 minus 2 square root 6 over 2 I. These reduce and you get square root 2 minus I square root 6. That's the best possible answer, not this stuff here. That's the best possible answer. But that's all you do, just simplify it. Multiply and dividing complex numbers. Now, you might be like, why do I have complex numbers? Like, why do we have it in triangular form? Like, what's the point? This is the point. It actually makes multiplying and dividing super easy when it's in triangular form. So, when you have to multiply, all you have to do is multiply the radiuses and add the angles. That's it. When you're dividing, you divide the radiuses and subtract the angles. That's all it is. So on these two, we want to multiply these. So we want z1 times z2. So first we're going to multiply the r's. So 6. And then we're going to go cosine, and we're going to add the angles. Pi over 4 plus pi over 3 plus I sine of the same thing. Pi over 4. 3 pi over 4. Sorry, not pi over 3. Plus 3 pi over 4. That does make it a lot easier, actually. But that's it. You multiplied these complex numbers. You just had to do that. And it really helps if you try to multiply like 7 in a row. Just keep on multiplying. It makes it so much easier to multiply complex numbers than it is in any other fashion. So let me simplify this real quick. So 6 cosine of pi plus I sine of pi. Like that. And if you want, we can go further. Pi is over here. -1, 0. So this guy is -1. This guy is 0. So you get 6 times 1, which is just 6. So that was 0, went away. But that's how you multiply complex numbers. It's so much easier when it's in polar form than when it's not. Another one, you want to multiply, so z1 times z2. So again, first multiply the 2 and the 8, so we get 16. And then here we're just going to add the angle. So 2 pi over 3 plus 11 pi over 6. That's a common denominator that later. And then I sine 2 pi over 3 plus 11 pi over 6. Like that. So we need, if we're going to add these, we need a common denominator. So let's go times it by 2 over 2. So we get 4 pi over 6 plus 11 pi over 6, which gets me 15 pi over 6. So let's rewrite this. Cosine of 15 pi over 6 plus I sine of 15 pi over 6. Something like that. I don't think we need a parentheses here. Now, you probably want to simplify it. 15 pi over 6, that does reduce, right? So 15 pi over 6 divided by 3 gets me 5 pi over 2. That we could graph. 5 pi over 2 is on the unit circle. Here's 0, here's pi over 2, 3 pi over 2, right? Because it goes basically 0, 1 pi over 2, 2 pi over 2, 3 pi over 2, 4 pi over 2, 5 pi over 2. So it's just the point right here of 0, 1, which makes cosine of that 0 and sine of that 1. So I get 16, 0 plus I, which gets me 16i. How about dividing complex numbers? Just as easy. So we're going to do z1 over z2. So that's going to be 24 over 8. Just divide the numbers. And then the English, we're going to subtract it. So top minus bottom, cosine of 300 minus 75 plus I sine of 300 minus 75. This gets me 3 cosine of 225 plus I sine of 225. Another one where you could simplify this, cosine 225, we know how to do that. Here's 180, here's 270, 225 is over here. We always go to the x to make a triangle. That is 45 degrees, so 1, 1, right, 2. But the sign was negative because we're going down. So cosine of 225 is just going to be adjacent right hypotenuse. So 3 times 1 over rad 2 plus I sine of 225, which is going to be opposite over hypotenuse. So negative 1 over rad 2. And then we get our answers. So that's how you divide, right? Just as simple as multiplying. So how about the power complex numbers? What if I want to take a power? We know how to multiply, but if I want to take a power, well, it's just taking a power is just multiplying by itself over and over again. So a mathematician named De Moivre noticed a pattern that if you do that, whatever the power is, it manifests here as the number next to the angle, the multiple of the angle. So like power 3, it turns out to be 3 theta, and the cube the radius is. Power of 4 is r to the 4th, and you times the angle by 4. So we call this De Moivre's theorem, which is basically just this. If you have this thing in polar or trigonometric form, and you want to take a power of it, z to the n, that power is going to go to the radius, and it's going to be the multiple of the angle. So let's do an example. So if I wanted to find 1 plus rad 3i to the 12th, by hand, it'll take me forever. Like, we don't hate that. So what we're going to do is we're going to make this into polar form. So I want it like this, or trigonometric form. Because taking the 5th power there is so much easier using the Moivre's theorem. So we're going to transfer this, and now we're going to write that, right? If I want to transfer this, I need 2 things. I need r, which is just square root of 1 squared plus radical 3 squared. So 1 plus 3, which is square root of 4, which is 2. And I need the angle. Tan of theta equals b over a, so radical 3 over 1. Where does it happen at? That's in the first quadrant. Rad 3, 1 is 60 degrees. So over here is going to be 60. So let's rewrite it. Z equals 2 cosine of 60 plus I sine of 60. Now if we use De Moivre's theorem, remember De Moivre's theorem is a trip. All you do if you want to take a power of something, like I want to find the 12th power of something, we're going to take the radius to that power, and then we're going to multiply that power times these numbers. So if I want this z to the 12th, it's going to be 2 to the 12th cosine of 60 times 12 plus I sine of 60 times 12. Which is going to be 2 to the 12th cosine of 0 to 720 plus I sine of 720. Well, we have here cosine of 720. So you have 0, 90, 180, 270, 360. If you go round again, you get 720. So that point there is 0.10. So x gets 1, and y gets 0. So I get 2 to the 12th, 1 plus 0i. And that's basically just 2 to the 12th times 1. And that is 4096. That is this number to the 12th power, 4096. That's the Moivre's theorem, and that's the lesson.